Okay, so 10 seconds passed, so we can start. So my name is Maria Prandini, and I have the pleasure today of introducing as a chair the final plenary speech, which is given by Professor Frank Allgower. So Frank is well known to this community because he has been a main contributor and he still is a contributor to MPC. He received many awards for his work and this effort spent for our control community at large. He was IFAC president in the triennium 2017-2020, received many awards like the main one, I will make it short because otherwise Frank have no time to give his talk, the Leibniz Prize from DFG, the German Research Foundation, for which he worked as a vice president. But most of all, I would like to recognize his contribution to this community in terms of founding this conference series. So I think this plenary speech is long due, and we look forward for your talk.
Thanks very much, Maria. I hope that works. Can you hear me? Okay, thanks very much, Maria, for this very kind introduction, and thanks very much to Moritz, Paul, and the other area chairs for having me here as a plenary speaker. And as I'm the last speaker, I should also say by now we know how the quality of the meeting here is, and I think it's exceptional. So a very big thanks and very high regards to those people who are organizing it, Toshi, Ken, Kenchi. It's really perfect. And lastly, having been to conferences for many decades, it's amazing how many people are still there on the last day. So also compliment to this whole group of people here that you really seem to contribute to our conference. So we had now 3+ days of interesting talks, very mathematical partly, also very much in the sense of that we are very precise of what we are doing. We define, make assumptions, then we prove something. Will change now. I will not do that at all. So it's at the end of the meeting, so it should be much more relaxing. And what I will do is I will take a view on our field, reflect on where are we coming from, where are we currently, and where should we maybe go. And I will do that, of course, not in a very general way, but in the way that the talk announces. So just asking the main question, is model-based or is it data-based in the future? Do we have to turn that motorcycle around and look in the next direction? So that talk will be more assessment, future directions, and this is also where our conference series comes from. It's the 8th conference of that type, and the very first one took place in 1997 at the location which is above the Lago di Maggiore, so a very nice location here, conference facility of ETH Zurich, and it's very difficult to get in there. You have to, if you're a professor at ETH, you can apply, and chances that you get in and have a conference there is very small, and usually it's 5 or 10 years ahead of time. We were extremely lucky. Somebody canceled the meeting, and then they were looking for a replacement, and then I said at that time, hey, wow, it's a good opportunity. Let's do that. It's a very different setting than we have now. So at that time, you didn't have to pay a registration fee, but your trip was paid. At least the hotel you didn't have to pay for. So no an inverse registration fee, I would say. Very nice setting. This picture you have already seen. It's the picture from Moritz. I stole it from the email that you sent. And at that time, NMPC was really at the very beginning. So if you, in 1997, the topic of MPC was there already, was actually there since 15 years already, but it was small. So 1,000 papers roughly published every year on MPC, which is a lot still, but if you count it, really if you count the papers that are on nonlinear MPC, it's 9 in that year. 9 papers that qualify as that. By the way, also 9 papers, it's a coincidence, on learning-based MPC. So at that time also neural networks were pretty in iterative learning control, so these were all learning control methods. So it was all meant as a one-time workshop, but then time went by and people said after this big success, hey, we should come together again as an MPC community and talk about things. And people were approaching me and saying, hey, do it again. And at that, I changed to University of Stuttgart in the meantime, and University of Stuttgart also had a very nice conference location. Zollernblick in the Black Forest, really this view that you have is from that hotel that you have, and that conference took place. And so we had the second workshop. The main one who did the work for that was Rolf Windeisen, just finished with his PhD, and then he organized such a nice conference. Then at that time, if you look at the topics, you will see lots of things that we are already seeing today. We decided then that we should have that regularly, so it should not only be twice or every whatever how many years when we find a nice location, but do it regularly. And so the next one was organized by Lalo Mani in 2008, and there we realized also it's not a good idea to do that just as a group of people, but you need a framework. So we decided we have to go into IFAC and make this an IFAC conference. I was chair of the technical committee 2.3 nonlinear systems at that time, and then you have a little influence, and so that workshop, our series, was taken over by IFAC, but it was not allowed to have it in 3 years because we were in World Congress years, and in World Congress years you cannot have a meeting, so we had the next one 4 years after in 2012, and from then on now we have this 3-year cycle which Mircea Lazar organized in the Netherlands. So this is the first really official IFAC NMPC workshop, and after that we had Seville, Madison, Bratislava, a purely virtual conference, and now here in Kyoto. So it's really great series that was very successful. Now let's see how things have developed over that period, so how MPC has developed since 1997. And we need a baseline for that, right? So we cannot just look at the number of papers, but we have to put it relative to something. And the relative thing would be publications under the topic framework of control. So this is how the control field evolved over those years. If you count publications with topic, so it's more general than title, it includes much more things, but also things that probably we would not consider our control fields. So, but it's roughly a good guess how our field develops, our total field. And there you can see, interestingly, that we have 3 periods, I would say. We have a growth period, a linear growth period, up to the end of the 2000s, to the first decade of the century. And there we had a fairly small growth, and since then we had a very large growth, and now we are completely flattening out. For whatever reason, so I'm also not going to speculate, maybe that's a topic for the roundtable discussion afterwards. So that's the baseline that we have. And now let's see how MPC develops. Just by looking at the MPC papers that you see here, you see, hey, it's exponential. Before we had linear, now we have exponential. Exponential is good, and if you do really the counting, the analysis, then the importance of the MPC field in terms of number of papers published, whether that is important, I don't know, but that number has increased by a factor of 4. So the relative importance is 4, but the absolute importance is still very small. We are in the 1% range of the control area altogether with our field. It's small, but it's growing very large. So now we are here for nonlinear MPC, right? Not for the general MPC. And that's the figure for nonlinear MPC, if you look at it. And now if you do again the computation, how that looks like, then it's growing exactly in the same way as the MPC altogether. So the ratio stays virtually flat. So nonlinear MPC and MPC grow in synchrony. Let's look at learning-based MPC. And I guess no one here is surprised. We see an explosion. So learning was around since all the time. So beginning 90s were also learning MPC papers, but now it is exploding. And in the history of control of MPC, definitely not for nonlinear MPC, we didn't see anything like that. No topic has exploded in that way, in such a way. And that's something that we should really explore, that we should really look at. Here is a little more precise way how to look at it over all the years. And the yellow curve is the interesting one. That's the ratio of learning database papers on the total number of MPC papers. And it's roughly at the moment every 4th paper, and still growing. So that is something that we should take a step back and think about it. What does it mean? So if every 4th paper growing, is that the new MPC? Is that the new thing that we have to look at? And that will be essentially the question I will be looking at. So why is that? Why do we have every 4th paper in that field? So there are 2 obvious answers, right, that anybody can give. Hey, learning is in this field, is exploding. Everybody is doing learning, so why shouldn't we? But I hope we are not so stupid that we are just acting like that and jumping in there, or at least not the people here in that room. The second reason why that could be really a good reason is we have no idea what our systems that we control do, right? So we have no model, so we just have to learn. But actually that is also not true, right? Because if you take the effort in doing an MPC controller, which is a lot of computational effort, a lot of safety things that you have to take part of, you would not do that if you have no clue about your system. So those 2 things are out, right? So they cannot be the reason for us jumping into that field at such an amount, every 4th paper. So what could it be? So, and of course, well, we believe that those controllers are better MPC controllers. That could be a reason. Now, what is better? In which respect do we talk about better? And if you look at the talks here, the plenary talks were almost all of them were talking about learning, right? So if you look at them, most people define better as better performance. And that is a good measure, right? So we could really make a conjecture. Database MPC controllers are giving us a better performance than model-based controllers. Conjecture, well, you can guess what my outcome will be. I don't think the conjecture is true, right? It can really not be. So in fact, I will make a counter conjecture. I will say the more information about the process we are having, about the process, the environment, whatever information, the more we know about the process, if we can use it in an MPC, we can use everything that allows us to predict into the future, the better the closed loop performance will be. So using more information will be better, not discarding information. Now, even more precisely, but still not precise, of course. So if you look at, we have a data axis and we have a model axis, and we have everything between no model and useless data to a perfect model and perfect data. It's kind of clear. If you have no good data and no model, hey, what can you do? Nothing, right? So you better quit your job and find a job with a company that has better control problems. If you have no model but good data, you go for database control. If you have a good model and lousy data, hey, also. So the decision what to do is kind of obvious in that respect. But I also think we can clearly see from that picture, if you are somewhere in the middle here, you have pretty good data and you have a pretty good model, hey, you want to use both. Why should you not use both, but not only the data and say, hey, I have no clue about what my model is. So use data and a model. And now if you look into the literature, which I did not, I have to admit, those tons of learning-based MPCs, they are hardly ever using both. It's usually, we don't know anything. We learn our stuff. Maybe you do a little bit physics-informed something, but you do not use really the model information. So I don't know whether that is good. So one last statement in that respect. So if I have to choose, somebody stands there with a gun and says, you can only do one, sorry, we have not money for both, you can only do one. I would always choose the model, because at least for nonlinear systems, and if we have to predict the future of our system, which we do in MPC, right? Of course, a model is so much denser in information that what you get out, you need lots of data, really amazing amounts of data for a nonlinear system to predict it. So you should always choose the model over the data if you have to choose. But if you don't have to choose, then you just use both. So here is an application study from our own paper. So this is a data-driven MPC method, the blue curve here, for a simple CSDR, very nonlinear system, but very small system. And this is the best performance that we can get. And this is from one of our papers. And we compare it to model-based MPC. And that's the curve for model-based. You have to jump from here to the set point up there. And of course, model-based is so much better. Hey, you know your system. How could you possibly be even close to it? No, model-based is good. If you have information, use that information. Even excellent methods than this one that we developed will not be able to do that, right? So it's kind of obvious. So I think this conjecture that we are getting something better is wrong. If we add the conjecture and say adding to our model knowledge some data, adding it, including knowledge that we can derive from that, then it's true. Then we can get a better performance, but not by choosing between the two of them. Now, okay. So this does, of course, not mean database control is bad and we should not do research in that direction. And even purely database research is a good thing to do because you need to understand it, right? So let's do it. So what can be our contribution? And let's face it, at the moment, out of also all those papers that I showed you, this explosion, our community is a very small piece of that share. So we have not grown in numbers. So this NMPC conference is not suddenly 10 times as large as it was before. Our community is the same, and the number of the papers that we are producing is roughly the same. This growth is people from other communities, namely computer science, robotics, that are getting into it. Now, why is that? And there is a very simple reason for that. We didn't see that with H-infinity, we didn't see it for nonlinear geometric control, for no other method did we see it. But for NMPC we see it now. Reason very simple. Hey, you can explain everybody what MPC does. Hey, you have a model, you predict into the future, you play around with your parameters, with your options, you pick the best one, you implement it, and hey, you want to do a feedback, so you not only do it once, but you do it repeatedly. That's MPC, and if you know that, you can implement an MPC controller. Try it out. ChatGPT is perfect in giving you an MPC controller that solves an MPC problem. You do not need a basic control course. Those people, no, not all of them, of course, but many of those have no knowledge. They don't know what a Laplace transform is. They don't know what the transfer function is, what a Lyapunov function is. The entry level for doing MPC, for applying MPC, is very low. So anybody can jump in there. Now, is that bad or good? I think it's very good. But if those people jumping in the field and are taking over and are saying, hey, MPC, that's not you guys, that's us. And Sébastien made on the very first day a comment like that. Hopefully they do not forget that we exist, he said. And there is really a danger, and I want to give you a little anecdote here. So there is me at a meeting, a postdoc at the Max Planck Institute we have in Stuttgart. You can easily see who is me by the hairstyle, right? So, and we were introduced, and I said, hey, I work in the MPC field. And then that lady said, oh, you're also a reinforcement learning person. Which is okay, yeah, but then she said, oh, that's cute that you use the old name for reinforcement learning. Well, I tell you, we didn't get friends. But this is really how it is, right? And let's face it, those people are not stupid. These are very intelligent people in that community. At the moment, they are attracting the best young people and in huge amounts. So there is another guy who is pretty good in that field, Jan LeCun. So he's the chief AI scientist of Meta, and he's Turing Award winner. He has the Nobel Prize in computer science. And this is a talk he gave at the Center for Artificial Intelligence and Robotics that he has, New York University in Abu Dhabi. I'm in the advisory board of that center, and he gave a talk, and then he said, abandon reinforcement learning in favor of model predictive control. Okay, I'm sitting there and thinking first, oh wow, great. So even he thinks so, but let's face it, that is not true. This is not true. He does not really know what model predictive control is. He knows what the principle of model predictive control is. He is a very smart guy and a very nice guy, by the way. This is us on that advisory board in a safari in the dunes. Really fun experience. But they don't know what that is. But they talk about it. They take it over. Reinforcement learning, MPC, it's the same. And it's a computer science discipline. And those control guys, hey, let them play around with their Laplace transforms. Fine with us. So that is really a very big danger that we are facing. Now, is there a contribution that we can take? Or is it really hopeless? Are we void and we should stop that series after eight consecutive conferences on that topic? And I think, no, that's definitely not the case. But what we should definitely do is think of what is really our strength. Where are we good at? And what we are good at is certifying properties of controllers, not implementing an MPC controller on a fancy problem, but that we do it in such a way that it works. We understand that it works, we understand why it works, and we have a feeling for when it might fail. This is the contribution that we have. And for that, you need that basic control course. Without that, you cannot get into it. And those people, they cannot do that. But we should do all these things and contribute to that. This is what ChatGPT says. If you say, hey, there are people in another community, they do controllers, they cannot give any guarantees, how would you describe that? That's the outcome of ChatGPT. I will show you also a picture of what ChatGPT says is a better future for us, but it's a two-line question to ChatGPT. So, message, we should focus on our strength. So we should really think the control theory of MPC. That's what is the core of our community. And that's what nobody else will easily be able to do. If the other people learn also that, then fine. But by the way, in Stuttgart, also the computer science people started doing control, MPC, not other control. And then I asked them, yeah, don't you need a control class? We have control classes. Your students can, no, that's not needed. We don't need control education. It's, yeah, let's face it, that's how it is. So, another question I would like to ponder on is, now we have data-based MPC and we have learning MPC. Two different things? Well, question mark. I'm not sure. It depends very much on how we see that. If we translate data-based MPC with that Henkel norm approximated systems and we do something and learning MPC we use out of the toolbox of machine learning things, then they are two different roles that we are having. But if we think more about it and especially think what it means for the future for us, which direction should we go, I believe they are pretty much the same. And I want to show you that, at least that I have a couple of slides that have some content with this data-driven MPC method that is based on the fundamental lemma where we showed the closed-loop stability conditions with Julian, Johannes, and Matthias. Now, for those who do not know, what's the fundamental lemma? The fundamental lemma is a way how you get from data a description of the dynamics of your linear system. So you have a linear system and you have an input-output trajectory and you want to use that data without doing an identification. Just use the data in order to represent what your system does. It comes actually from persistence of excitation. So how do we have to excite our system? What input to choose in order to have meaningful data in our system? Because if you put into a linear system a zero input, you get a zero output. You can measure for a long time and you will not get any information about the system. So that's what it's all about. In the original paper by Willems and co-authors, they say, hey, use your data, your input data, just stack it up in columns of a certain form to form a Henkel matrix. And then if that Henkel matrix has full row rank, then you have a persistence of excitation. The real result is much more complicated. It depends on how many dynamic modes you want to identify and so on, but for simplicity. This allows you to characterize when you have a good input. But that is not the main thing. That was also not what the authors at that time realized, but you can use that thinking, that representation of data in a Hankel matrix, just filling it in, you can use in order to represent really your system dynamics. So you have a persistently exciting input, and output that results from that. You have a linear system, you don't know the linear system, it's unknown, then you can really characterize all the dynamics of that system using Hankel matrices. So if you do the same thing, filling up this Hankel matrix, not only with your input data, but with your output data. This is the HL of U and the HL of Y. So this is a constant matrix, just a constant matrix. Then the span of that matrix is exactly the dynamics of our system. So if you plug in an alpha, you get a trajectory of the system. If you have a trajectory, there exists an alpha that produces that trajectory. So it's a representation of our dynamical system. So writing that equation down here is if you want a model of your system based on data. Or what you could say, and that's my claim, this is we learned a model. Of course, a machine learning person would say, you are crazy. Where is your learning algorithm? No, well, if you define learning as acquisition of knowledge about the dynamical behavior of our system that we want to use for prediction in MPC, we want to get knowledge to find the future, and we collect that through data. That's learning. That is learning. That is a learned model that we are having. So there is no real difference between data and learning, only if we are stupid enough to translate learning into using machine learning tools. No, and that is very restrictive, yeah? We would also not do the same with our optimizers and say, Moritz optimizers are very bad, we choose some other ones, Larry Bicklers. We would not do that, right? We say they are both there and they are both pretty good, and we use sometimes one, sometimes the other, right? So, this is learning. And now, if we have a model representation, a learned model of that sort, we can do all different kinds of things. We can do a system analysis, and lots of people have contributed to that. Actually, that's a very outdated list here of, on that basis, what properties you can analyze. There you can do lots of controller designs, H infinity, L1, you can LQ, LQG, you can do lots of things on the basis of that learned model. And you can also do, of course, MPC. So you can just use in your MPC optimization problem where you want to minimize a quadratic cost function, as we usually have around the steady state that we are considering, and the only thing that we are assuming, we're having data that we are putting into our Hankel matrix description, then we can use that Hankel matrix description in order to predict our output. Because if we plug in different alphas, we get different trajectories in our system. So we can get information about the future of our system, and if the input was persistently exciting to get this model, hey, we have everything known about our system. And the only thing that we need to do is now also optimize over that alpha here. And we can do all the MPC, so we have to measure our state, where we are. That's an input-output formulation. No state. We don't even know what dimension the state has. Is it 10, is it 100, or is it 27? Maybe 27.5 or something like that. Yeah? So what do you do? So you cannot measure this state, but what we are doing, so I'm in the way, I'm moving to the other side and block other people's views. So there is what can we do? So we just include in our description here past data. So we collect what we have done in the past. And now if we know that in the past, so the t minus k, in the past, at least n steps, n being the dimension that we think in the worst case is our system having, our system is known, then we know everything about the dynamics. For everybody in the audience here, this is absolutely clear. If you have so many steps in the future, in the back, you know that you know everything about the dynamics. For a computer science person, they would say, that is bullshit, hyperparameter, let's play around with it. No, there's a clear explanation for that. So we have to pick as many steps in the past as our model can possibly have. And of course, that is very much related to our persistency of excitation assumption that we have up here. So we initialize our system. Hey, and note, it's an input-output MPC. So no observer needed. It's really input-output, which is pretty tough to get an input-output MPC controller. And of course, you can also add the inputs and the output constraints. And then if you predict into the future, we do our normal MPC stuff. We not only optimize once, but we optimize at every step over that thing, over a certain prediction horizon, as much as you have computation time available to do things. Now, that is not our idea, definitely not. So that idea was introduced in 2015 by some guys from Shanghai Jiaotong University in that paper here, which is really worthwhile reading. So they had the idea, and there were even a couple of more papers, but it got really only popular in 2019 by a paper from ETH Zurich, Data-Enabled Predictive Control in the Shallows of the Deep Sea. So, which is a really nice title, right? So, really funny title. Unfortunately, the name stuck. So, some people are using the word deep sea, and you should not. You should really not. First of all, it was a joke, and a very good joke, I have to say. I was laughing loudly when I saw it, but it's a joke, and it's distracting from the fact that this is an MPC algorithm. There you are really giving, like in soccer, you're passing to your enemy in front of your own goal ball and saying, hey, kick it into my goal, it's yours now. No, it's an MPC algorithm. It's a data-driven MPC algorithm, and we should call it this way. Lots of research going into that direction. Question is it a good method? So if you apply that in practice, does it get you somewhere? Well, no. And again, in that audience here, again, I don't have to explain that, right? An MPC is not guaranteed to be stable. If you choose your prediction horizon wrongly, if you choose things bad, and this is an input-output framework, we can talk about non-minimum phase systems. It's easy to find examples that destabilize, and everything looks good. Our 4-tank system that we have in the basement to educate our students in the basic control course, really the one that the computer scientists don't have. And I guess this is recorded. Maybe I should change my language here. So I was forced by the organizers to say such things. It's not really my opinion. I'm only conveying. No, of course not. Yeah. So, but it's destabilizing, yeah, or it can be destabilizing. So you have to do something. If this is a nuclear power plant, hey, no, we don't want to have that, right? Otherwise, we go back to that picture that DAL-E produced. So we need stability guarantees. Now you could also say, oh my God, everything starts from new. It took us 30 years or 25 years before we understood how to analyze model-based MPC, how to get those ideas. Now we have to go through that nightmare again. No. Exactly the same concepts, exactly the same mathematics works, which the message is, hey, that's good news, isn't it? This basic control ideas, this system theoretic knowledge that we have, it works. It also works in other contexts, now in a completely data-driven context. And now what's the easiest way how to stabilize an MPC system? Zero terminal constraints, right? That is the easy thing. So you add zero terminal constraints. So at the end of your prediction horizon, you want to be at your steady state. Now, okay, state, we don't have that. So we have to be at the steady state for at least as many steps as the order of our dynamical system has. If we know that for sure, then we are in steady state at that point. We add that to our system, and now we could say, okay, proving it will be very difficult. No, it's possible to prove. And it's the same type of assumptions that we use also in the model-based world. I'm not going to read it. You can look at it yourself while I'm talking. It's the same type of assumption that we use. And the result is also roughly the same. And the proof, by the way, except for a couple of technicalities, goes also very much along the same lines. So we assume our assumptions hold, then we can prove that if our system is feasible at initial time, it will stay feasible, recursive feasibility. We can prove that all constraints are satisfied in closed loop for all times, constraint satisfaction, and we can prove that in closed loop, not in our prediction. That's also an experience I have with another postdoc from that institute. Hey, you cannot trust your prediction in the future. If it goes towards your origin, there's no guarantee that the closed loop does that. Hey, We know that a prediction in over a finite horizon in open loop is not giving you the real result. But here we prove that in closed loop it converges exponentially. So data-driven MPC can be done. You can include output constraints. You can do many things. And now, of course, you say, hey, but zero-terminal constraint MPC is a very bad concept. It's very restrictive. You can go to terminal ingredients. You can do everything you want with that model. Pick your favorite question from the model-based world, and you can prove it. So you can find the typical terminal ingredients from quasi-infinite horizon. And Hong Chen is sitting in the back, who did her PhD thesis the first time for the nonlinear systems, the proof like that. So it can be done, and all data-based. So you can compute the terminal ingredients based on data, not assuming you have a model there. So all is possible. Now the computer science guys, and I really am not sure whether, did I give my signature, Toshi? I think ours. So they would say, but it's trivial, you have no noise in your system. If you have no noise, you can do your Laplace transform magic and everything works. Hey, let's add noise. Let's add noise to the data that we are measuring offline to fill our Henkel matrix. Let's add noise to our online data, and let's assume the noise is bounded. So that's something we have to do. Assume that the noise is bounded. Then our representation with the Henkel matrix is not true anymore. If you have noisy data here, if you get measured data over there that has noise. So you have to introduce a slack variable. And of course, if you make your sigma large enough, it will always hold, but then it's meaningless, right? So you want to have something where your sigma is as small as possible. What do we do in MPC if we want something? We add it to our cost function, right? And so you just take a term and add it to your cost function. You have a second regularization that is motivated by mathematics, regression analysis. So what you do is you just add these terms to your cost function, and now you have this sigma additionally as an optimization variable in your system. You have noisy data here, you have noisy data there, and you can use that. So we are still in business, but now does it work? Well, let's look at it. It's an additive disturbance that we are adding to our system. That's something we know in control, and especially in MPC, how to deal with that. And we have parametric uncertainty. So you can, again, take our machinery of system theoretic knowledge and apply it to the problem. Under certain assumptions, we prove, and you guessed it, recursive feasibility, constraint satisfaction, and of course stability. Now with noise, you are not getting to your origin exponentially, but only to a neighborhood. That is, the size of that depends on the amount of noise that you have. So again, everything works. This was considered as a very nice contribution, got an award. But the main message here is really our methods, our thinking, our systems theory work perfectly well also in the data-based world. Only if you introduce a neural network, some machine learning algorithm, you are running into trouble. So think carefully whether you want to do that. Then it gets much more complicated to do things. I'm not saying it's impossible. Maybe it can be done. But if you don't, we have ways of how to deal with that. So knowledge of control theory is useful. We should keep that basic control course in our agenda. So now, again, so far linear MPC. This is a nonlinear MPC conference. You can also add nonlinear, and I go over that very quickly. So we have our original data point. We want to go to our set point, and on the way we are collecting trajectory information. So this is our current time. So we are having online information that we are having. It's noisy online information that we are having, and we know the inputs that we excited. So in our MPC formulation, why not use that? So why not just look into how our system behaves along the trajectory that we are doing? We would say linearization based, so we do that along, or maybe we do some adaptation. You can guess what I'm saying in a second. It's an online learning that we are doing here, right? Because it's the same. We are learning the model from that. So we just plug that in, so we constantly change that information, and then with this online learning, we can get a next step. But in order to prove things for now a linear model-based, a linear data-based approach, you have to prove something for nonlinear systems. So you need to go one step further. But the message is, again, We have tools in our community. This time, artificial intermediate set points. Daniel Lemon, who is unfortunately not here, and co-authors, they have introduced that 15 years ago, and it's really a very nice concept. So what you are doing essentially is, if you go along your trajectory, don't try to get immediately to your reference point. Go to something in the neighborhood of steady state manifold of your system. And then if you add that information, that artificial reference on your manifold, for which you don't need any data, because with this equation down here, it's just again saying, hey, we have we are at steady state, plus it guarantees you stability. So two things at the same time. Then we get now a problem that is still just a strictly convex QP, and it can now address nonlinear systems. And surprise, surprise, you make a couple of assumptions, you can prove recursive feasibility, constraint satisfaction, and some stability guarantees for your system. Again, the proof here is much uglier, so that's not really a very nice proof, but it still relies on all the things that we know from our community. So we can deal with nonlinear systems also, and we give guarantees. Again, our thinking, the knowledge that we have, that makes our community is good, and we should stick to that knowledge. That's the strength we have. Other communities do not have that, and it really also works in practice. I'm skipping that and rather present something else. So this was the starting slide, right? I said, okay, why do we do database things? Why do we learn our model? Because we believe that they are better. Now, better so far was performance. Now, you could also have a different better, right? And one better that we could say that makes a lot of sense for our community, let's use the data to be better able to prove something about our system. Let's use data to certify system theoretic properties. And I think that's also a better controller, if you can assure that later on that controller will really work. And now I'm showing you a couple of slides on a data-driven min-max MPC problem, only for linear systems, no extension to nonlinear yet for that system. That is the PhD work of Ifan Shih in my group, and it's also together with Julian Berberich. So what we are looking at is min-max, robust control, now over an infinite horizon. So are we shocked by infinite horizon? Isn't that MPC anymore? No, we are not. That's the problem we want to solve, right? The finite horizon is only due to that we usually cannot compute the infinite horizon. So it's not a feature, it's the curse, or actually something positive that gives us all a lot of work over the last 25 or 30 years. So, and this was inspired by a paper by Kothari, Balakrishnan, and Murari from 1996, where they have shown for linear systems, you can solve this min-max problem. So you minimize your input trajectory over all your model representations that you possibly have, minimizing this objective function, and your prediction is done with an AB that you do not know. You just know it's in the AB here. You have your constraints as usual, and now you want to solve that problem. And what the main observation at that time was, you cannot solve that problem, or at least not easily solve it, with open loop controls. What you have to do is policies. So you minimize over policies, and the policies change over time. So at each step you get a different controller. F, that's the solution of your MPC problem, and then you can compute what you are plugging in. Now in that paper, they were assuming that this model set AB is known, this C is known, and it's a polytopic set, a known polytopic set. So, and then this problem can be solved using LMIs. Now we want to look at that problem, we don't know that set, and we want to get it from data, this set, and then solve the same problem, right? And I want to show you how that is done. A completely different approach, no Hankel matrix will appear here. So we have our linear system, we are again collecting data, this time input state data that we are collecting. We don't know our system, this time we know the dimension because we assume we have state feedback. So in order for that you need to know how many states you have. we have a noise on our system, and the noise is of course unknown. We don't know the noise at each step. It can be anything. The only thing that we know is that the noise is bounded, an L2 norm bound on our system. Now, can we get with that information, can we do something about proving or solving that problem and proving that it leads to stability? And indeed it can be done. Just think in the very simplest case, we just have one data point at a time point I plus the x at the next step, so only 3 values. If the x is a vector, the u might also be a vector, so but only at one time point, then you can solve your equation for the noise, right? You don't know the a, you don't know the b, you don't know the omega, but you know the x plus, the I plus 1, the xi, and the ui. So you can solve that equation. Now we have that assumption that the noise is bounded. You plug it in and you get a quadratic matrix inequality that describes your system. So the thinking here is one data point, that this characterizes all the ABs that you can possibly have that are consistent with that data. So it's all possible ABs. How many ABs would that be? Huge. If the noise is big and we only have 2, 3 data points, right, then we have a huge set, and we know the true one is in between. But now we not only have one data point, we have whole sequences of data points. We have trajectories, and we do that for all those data points. So essentially you're shrinking that set of possible ABs that are consistent with the data that you are observing. You are shrinking that down, and you can characterize that set, again, without going into any details, by another quadratic matrix form that we are having. So this is the description of all the ABs that we can possibly have. Now, if you want to use fancy wording again, hey, we do a learning here, and this time we are learning the uncertainty set of our system. But a more precise definition would be we are characterizing the uncertainty set, and the better we learn, the less big this set will probably be. And now we can solve again the problem, or we can think about solving that problem. We want to minimize over our input trajectory, over all the ABs that maximize our system. It's a game, right? So our objective functional, subject to our system, where we don't know the A and the B, where we have our constraints, and now what we know is that the AB is in that set described by this here. And now we want to find a feedback, changing feedback policies over time that minimize our objective function. How can that be done? Again, no magic. This is what you would immediately think of if you are an MPC person. So you are trying to find a value V that is upper bounding your cost function for all the ABs that you have. So that's what you want to have. So we have a linear system, so let's look at the quadratic V, for which we don't know the P, and for all the ABs here, this equation has to be satisfied. Now, for all other communities, you have to explain what that equation means. The V goes down from the next step, goes more down than the stage cost function is. Here, I guess everybody has seen that. That's the key to our stability proofs, to almost all our stability proofs. And now we are asking, can we find such a V for which we can assure for all the ABs that this is the case? So now you sum that up from 0 to infinity, which is also what we always do, and then you get this equation. It says the maximum over all B is bounded by this V at the time xt. It's an upper bound. So this characterizes our upper bound. So if we can solve that equation here, if we can find such a P and an F, the feedback, the policy, then we have solved our problem. Let's plug in for the U, our U equals Fx. And let's plug in for the V, our x transpose pt. Then we get this equation here. It's not an LMI. It has products of unknown variables f and p. So, but this equation characterizes our problem. So finding this f and the p that solves that problem here is a solution to our problem. Unfortunately, a non-convex one. And now you can use the standard LMI magic convex robust control magic to do things. So you redefine your unknowns. You go from the P and F to an H and an L. You use sure complement in a number of times. You use S procedure. Everybody in the robust control knows how that is being done. And then you can reformulate your problem, and it gets to the one on the left side. So that you minimize now over this gamma, which is the value of your upper bound. That's the cost that you are getting, the worst case cost over all your AB. This first set of equations here, this gives you the description of that value over your A and B's. The second two ones are our constraints, reformulated as LMIs. And if we solve that problem, then we are getting a solution to our problem. So we are getting one H, L, gamma, and from that we can compute the F, and from that we can compute the U. Now, do we do that in MPC? Just find the feedback and then apply the feedback? No, we don't. And also note, here is the xt in there. That's our measurement that we are having. Of course, you can say I start out at an x0, compute a constant F, and I apply that for the future. Might also work, or actually will work. You can even prove things for that, but not really good. What we do is, of course, a receding horizon solution, an MPC solution. We measure our xt, plug it in here, solve that problem, get an F, apply that F, apply the U that you get as the first step of that F, discard all the other U's, apply it, move one step further, and then you redo your computation now with the new xt here. And this way you get a closed loop solution. So it's an MPC solution for the robust min-max solution that we are having. And now again, the good thing, and that is what I think is a necessity that we have that for our things. We can prove that it works. At least for linear systems, we can prove it. So if we have a solution to our SDP at the very first step, then we can prove that we are recursively feasible, that we satisfy all the constraints, and that we converge to a neighborhood of our origin, and the size of that neighborhood is related to an RPI set that depends on our noise that we are having on our system. So really, again, no real magic here, even so I'm not explaining how that is done. It's worth reading the papers. I give you the QR code on the last slide if you are interested to look at the papers, but it can be done, isn't it? That's amazing. We have no model information. We just collect data. Now we learn the uncertainty description, and we can certify that this really works. Not going into the proof. Now, we only used offline data. We can also use online data. We do that, and we collect the data that we are having. So why not append that knowledge to our description of the uncertainty? So we append with every data point that we are getting, we get new information that we are adding that. Well, of course we can do that. Hey, it's an online learning of the uncertainty set that we are doing. Learning data, it's the same thing if you interpret learning as not using machine learning tools, but knowing something about our system. And then you can apply that also. So the only difference is here, that second term that we have here in that equation, and another line here, which I'm not going to explain. So the MPC problem is still the same, and for that you can also prove that it is working. Now that's for linear systems, but Ivan's PhD is on solving the nonlinear problem, so stay tuned. I'm pretty sure we have a number of ideas that this can be extended to the nonlinear setting as well. So let me conclude, and Moritz, I'm almost in the time that you gave me, which is less than I originally had. So what do I want to convey? Don't do pigeonholing. This is a word that I had to look up, actually. In German, it's Schubladendenken for the Germans here, 26 Germans. So Schubladendenken. Don't do pigeonholing for your methods. So data doesn't mean Henkel norm, and you need to do something in that pigeonhole. And learning doesn't mean you have to apply learning tools to your system. Does not mean. Learning is getting information about our system. Let's be flexible. Let's be especially creative. And data doesn't mean putting data in a Henkel matrix, but data means we have measured data offline, online. We do something with that data. And what we do with that data, I showed you two methods, and both said, for example. There are tons of other ways you can do, and a very interesting way, now I see Daniel here over there, he was using data and learning in a completely different context. So you can do lots of things with data, and you should. So think data, don't think tools. The tools is something where we should restrict ourselves, or not restrict ourselves, but we have our own control tools, and those we should use. So that's the first message. The second message is exactly that. So we are good at certifying closed loop properties. And I stress the closed loop here also. Yeah? If you have a proof that something works in open loop, hey, that's no proof. In MPC, you need a closed loop proof for that. But we know how to certify system theoretic properties of all different kinds. So use data and models, and preferably really both, and think about how that can be done in order to be able to prove something. Then we really have a contribution that is meaningful, and we can be really creative, and we can, as a community, have an impact. Then we have better MPC controllers than other communities that may have fancy learning algorithms that are working really nice. Now, if I look at this conference here, I'm actually a little proud. So not every one of the presenters and papers here belonged to the little village of Asterix, the Gauls. I'm not sure, is that known to everybody? So they are a little village, were fighting the Romans, and guess who won? Or who always wins? They are still winning. So we are small. Machine learning community is huge, is really growing. They are the Romans. Hey, but we have tools and things that we can contribute. And really here at that conference, people were mostly looking into things that were provable. At least they said, and the next step would be that we have to prove things. And that is good. So that is really very much reassuring. So now last question that I want to look at is we have this tremendous explosion of data. MPC, learning MPC. Do we need more of that? So should we all now be very much encouraged to make this quotient from 0.25 to 0.9 and only do data in a very creative way, okay? And we have system theoretic properties, and I don't think that this is a good idea, right? So I think data is good if you add it to your model. A model is better, and if you use both, it's really the best. So we should not stop doing model-based MPC control. And I want to show you that with the group members in my group, in the MPC group. So Ifan is a data-based MPC person, but she's the only data-based MPC person. No one doing Henkel or something in my group. So what we are doing at the moment is stochastic model predictive control. Henning, who is unfortunately not here, is computing to stochastic model-based predictive control. A very important topic, very interesting, very unsolved, I would say. Lots of things going on. Matthias, who is here, he has had a poster at the conference. He's doing distributed MPC based on models, and you can even combine the two things, and that's Matthias, who is also here at the conference. He is doing distributed stochastic model predictive control, model-based. Now, Niklas, together also being here, actually the whole group except for Henning and Ifan are here. He is doing robust model predictive control, now with the goal to not only have our classical parameterized uncertainties, but like we have in robust control, that you have dynamic uncertainties. You want to really do the same thing that the robust control people are doing, which is or was the PhD of Lukas, who is finishing very soon, and many people here know, and Niklas, who is here, is continuing that work. And lastly, Jonas, also in the direction that we have followed in the past, is working on economic model predictive control. So you see, I'm not putting all my eggs in the database basket. In fact, only one egg is in the data basket, and all others are in the model-based case. So let me conclude. This is promised the last slide. My suggestion is we focus on our strengths. What are our strengths? We are good in math. We are good in systems theory. Let's prove things. And let's also be strict if people submit papers from other communities to our conferences, to our journals, we should apply the same standards that we always do. Like they also do for our papers. If you submit to NeurIPS, to ICL Art, and so on, you get the standards of that community that you are judged with. We should do the same. You have a contribution in nonlinear MPC or in MPC altogether, MPC theory, if you prove something. If you don't, hey, nice, proof by example. It worked, nice, very impressive, but not really something that we should care too much. But of course, that doesn't mean we should not be open to new stimuli. And now the podium discussion will be about what is in 2030. Maybe data, probably not. I would guess the next AI winter is pretty much coming, and then people are losing their faith in that, so we should be open. What's coming? But this we should include and add to our community. Not move our community, not making us a part of the machine learning community, but include knowledge that we have from other communities into our own way. And if we do so, I think we have a bright future, and we will have many more NMPC conferences to come. And I promised you that I asked DAL-E and show you what that is. So how does our bright future look like if you do that same session? So it knew that talking about model predictive control and about dangerous controllers and so on. And that's what DAL-E thinks the future looks like. Obviously, if you have plants on the platform of your trains, that is a very positive thing to have. So, with that, I thank you very much for your attention. Here is the promised barcode, and I'm happy to answer questions. If there is time for questions, well, not much, right?
So thank you very much for a very inspiring talk that I think it's useful not just for students but also for more experienced researchers. So yeah, we have limited time, but I would like to ask at least 2 questions. So Eric?
Okay, yeah, I don't know if this is a question for now or the panel discussion, but control is sort of a postgraduate specialization, and most of us probably come from a traditional engineering background, whereas computer science is an undergraduate not specialization, and so there's many more of them than us. So I guess that's one thing which is very difficult to overcome. But I spoke to a colleague of mine at Google who says they know they have control problems, but they won't appoint a control engineer because we don't have the skills that they need. So how do we get those skills, and how do we communicate with them?
Okay, very good question in my opinion, but I'm the wrong person to answer that. Or I would say again, the answer is obvious. Let's add to our community, to our education, these skills that are needed for that community. Hey, we cannot ignore that community. So they won't take control classes. They won't hire even control engineers. So, but let us, we need to know. And actually, that's what we do. If I look at the talks here, we learn how to use machine learning tools. We learn that stuff. So we know it in the future. And that's what we should do. No, but very important, yeah, and very disappointing. So I'm using not Google anymore. Firefox, much better.
Thanks for the talk. My question is the following. We said that we should use first-order principles, our models, in our algorithms, not only the data, right? Do you think maybe one day we can employ algorithms to derive all of these principles? Because as a human being, our, for example, physicists are, how do I say, coming up all of these principles, and it's not a reality, it's just a model of a reality. And yeah, do you think we can employ algorithms to?
I'm not sure whether I understood the question, but if the question is, hey, modeling is difficult, yeah, it's true. That's why we are all engineers from the different disciplines, right, Eric? So that we learned how to do the modeling. But yes, sometimes it's difficult. Some slides I skipped. We had a problem together with our neighboring institute where we were not able to model something, and then you have to use data. Hey, but we have a history of 40 years, more than 40 years in looking at that problem. It's called identification. And it's very intelligent people have been looking at that and coming up with solutions. And also nonlinear identification, very difficult problem. Same intelligent people don't have a really good solution. So yeah, maybe if you cannot model, you need to do something. You use your data, but there is a tool already, identification, that you can use, and we can make that better. But if you know something about your modeling, and it's also if you solve a control problem, right? If you're a practitioner, you know that doing the modeling is 90% of the time, probably 98%, and 2% is doing the controller in the end. Yeah.
Thank you.
Hello. Yeah, if there's still time for one question, I have a technical question about the slides. So I really enjoyed your talk, but I have a, let's say, a question and a concern with Willem's lemma. Can you go to the, I mean, it's not a typo, it's a philosophical question, to the problem where you have it formulated maybe for the nonlinear. I think that was the nicest, with the sigma and the alpha. Somewhere, here. So, my concern or question is the following. In some sense, we choose sigma and alpha, right? So they are both decision variables. And at the end, if we want to interpret it, we want to know u, right? The u trajectory. And the alpha is many more parameters than u, if I'm not mistaken, even after adding the constraints.
Depends on the size of the data you have.
So, in particular, when you have noisy data and nonlinear systems and so on, my concern is the following. So somehow, if you would fix the initial conditions and you remove objective functions and anything else, and then you look at all possible trajectories that you can reach, it's not one trajectory, but it's, so to say, I mean, even if you fix the controls, it's a, so to say...
It's a one-to-one condition. For every trajectory, you have one alpha. Of course, you can have different Henkel matrices. Yeah, so if you change your data...
I think you have one alpha, that's for sure. But let's say if you want to, let's say, usually when I have a deterministic system model, I fix a control trajectory and I can simulate one trajectory. But because I have, let's say, noisy data and I have interpolation possibilities, it's somehow a convex hull of possible trajectories which I generate. Which is, from my point of view, when I optimize, I always teach, let's say, my PhD students, don't let the optimizer play with our modeling errors, and somehow playing with the sigma and the alpha is somehow is optimistic, so to say. So we allow the optimizer, and I wonder if we shouldn't maximize with respect to at least alpha. No, that sounds a bit strange, restricting it maybe to some control trajectories. But so what's your comment on that? So I don't know if that disturbs anyone apart from me, but somehow for me that's disturbing.
You talk about that alpha here, right?
Sorry?
Yeah. You talk about this alpha.
Yeah, the too many degrees of freedom, that the data, so to say, that you interpolate basically possibilities of that could happen. Let's say I observed 2 times the same input sequence, right? And because of noise, 2 times I got different y's, and now I choose the one that is better for my objective. But why? I mean, why should I choose the one that's better for my objective? That's too optimistic from my point of view.
But I don't think it's true, because, you know, we have a lot of decision variables, yeah? We add some decision variables, but we also have constraints.
Yes.
These are our constraints that we are having. And those constraints, the model, the measurement, and so on, the true constraints, they restrict my solution. And they restrict my solution to exactly those that make sense. So I don't think you have a degree of freedom. The moment you fix your Henkel matrix, the moment everything is done, because it's a one-to-one relationship. One alpha gives you one trajectory. It's one-to-one relationship. You plug in the alpha, you get exactly one trajectory. You have the trajectory, and if you have a full row rank H, which we assume, then you get just exactly one alpha that solves that problem.
Yeah, I try to phrase it more in like numbers of constraints, but I can't do it now. So I'd like to follow up. It's really, yes, it's a concern I have.
It's not showing. It's really not showing. You get a solution, you get a unique solution to the problem, and it's a quadratic problem, right? Mm-hmm. So it really has all the features of the quadratic problem. And even if you were right, Moritz, which may be true, but even if you were right, I would say, hey, the main contribution is the stability proof, and that doesn't hinge on that.
Yeah, and maybe a mini detail, which is really only technical. Don't you want to normalize the alphas to be summing up to 1 and be positive, basically, so that it gets a convex combination in case you have a...
You cannot do that, because, you know, this is physical quantities. The U has a unit, the Y has...
you have a nonlinear system.
This has units, this has an absolute size, and you better also normalize everything beforehand, like we always do in practice, right? But they have units, those things. So you cannot just say, hey, my alpha here are summing up to 1. They are not. So this is the true trajectory. If you plug in a true trajectory, here it's the predicted trajectory, but that's a trajectory of your system. And now if you multiply that with 1 alpha, you get exactly that. Yeah.
Okay, we'll follow up.
Yeah.
Yeah, thank you.
Okay, thank you very much. I think that many of us, including me, would have questions, but we can keep them for later. Okay, thank you very much.